Afternoon. So I'm going to talk about bare metal provisioning with OpenStack. It's a new feature being added. Most of it's in trunk right now. It wasn't in the last release. A couple teams of people working on this, mostly a bunch of us at HP, some people from NTT and ISI and other groups. Why is this interesting? Well, when you've got the ability to stand up things in clouds, there's a bunch of tools already out there to do hardware provisioning. People are working on mass and crowbar and so on. But there's also tools to orchestrate standing up lots of instances in clouds. And if we just use the same set of APIs to control both of these, things become simpler. Why rewrite tools? So, reuse. There's also performance. There are lots of different types of applications that like to run on physical hardware directly, like InnoDB, databases, or things that need access to specific PCI cards that aren't virtualized. So being able to deploy these onto physical hardware using the same API that you would stand up a cloud instance. Pretty nice, we think. And then this also opens up some new possibilities. When you've got the ability to already orchestrate standing up large numbers of cloud instances, and then you replace the backend and you can stand up lots of physical instances, you can suddenly orchestrate deploying large numbers of physical machines in data centers. So what exactly is it that I mean by bare metal? Well, it's a hypervisor driver for Nova. At this point, everyone should know Nova is the compute abstraction layer for OpenStack. So there are hypervisor drivers right now for Zen, KVM, LXC, Hyper-V, other things, and so on. And this is like those. It fits in the same place in OpenStack, but it's different. It's different because it's not actually a hypervisor. There's nothing else actually running on the machines. This is kind of a little cheesy diagram of what Nova looks like, or a Nova compute host. You've got physical hardware, and you've got the operating system running on it, and the Nova compute agent. And you've got some hypervisor. And the compute agent is sending commands to the hypervisor to do things with VMs, like start them and stop them and snapshot them and so on. And that's all pretty normal stuff. And then you've got on your network a bunch of these Nova compute hosts and some control plane with OpenStack services that people have talked about at length. So yay, normal Nova compute. With bare metal, things are pretty different. We're abstracting the idea of hardware. So you've got, on one host, your bare metal compute agent, which is just a Nova compute agent with a different driver loaded. You've got a physical machine with an operating system and your user space applications, whatever those might be. That's basically the equivalent of a VM, but on physical hardware. And we're using PXE and IPMI to control this. So you've got a control plane, a Nova compute agent, and a bunch of instances. These are now Nova instances, but physical hardware. And maybe your network is really big, and you've got a bunch of bare metal Nova computes controlling lots and lots and lots of hardware. Great. That would take a lot of work to set up right now. It's not quite as automated as some of the other stuff. Is there a simple way to do this if you just want to play with it in a lab? Yes, there is. I don't think anyone's talked about DevStack today. Not really. So DevStack is an opinionated bash script that stands up everything you need to run OpenStack on one host in kind of whatever people have thought the best, simplest, quickest way to do that is. So starting with DevStack, you load some customized images, basically just Ubuntu Cloud images or whatever cloud images that we've changed a little bit. You inform DevStack of your hardware. That'd be your MAC address, the number of CPUs, the amount of RAM, and so on. And this is what we're going to call the bare metal bootstrap node, because you use this to bootstrap everything else, all the other hardware that's currently maybe powered off. How does that actually work? Right? You've got one machine with all this information and running its own cloud, DevStack, but it's basically an OpenStack cloud on one box, and a whole bunch of hardware. It's powered off. And we're going to deploy those images onto the hardware and turn them on and then run stuff in them. It's a little bit complicated. So starting from all the stuff I just said, when someone might issue no boot, or you go to the Horizon API and you click Start Instance, what will happen that's different in this situation than in a KVM or Zen or regular virtualized situation is the Nova Compute agent is actually going to download all the images locally. Currently, it does some injection. We're going to remove that. It's going to build a TFTP config file based on the MAC addresses that it knows about from that hardware. Then it's going to send an IPMI command to turn on the box. The box comes up, DHCP request. It gets sent a special kernel and RAM disk, which are going to mount the local disks and expose them as an iSCSI endpoint and ping back to the Nova host. Here's the target you can use. The Nova node, there's an extra service running there for bare metal that is going to receive that, mount those over iSCSI, and copy the image onto it, and then send a reboot command back. And then your bare metal node, I'm pointing in the wrong direction, sorry. Your bare metal node is then going to reboot into the user image, whatever that might have been. Your application, maybe it's just an Ubuntu Cloud image with a Puppet client or a Salt client pre-installed. And hey, it joins your cloud and it kicks in, it gets a host name and IP and does stuff. We've got lots of plans. I mean, this gets really cool over time. It's still pretty young. Firstly, I want to improve the performance of the whole deployment. Right now, not scalable in a couple places. So it'll work well on a small scale. We haven't really tested it, but I'm sure that it's going to break with thousands of nodes right now. Because these things are creating a single point, a big bottleneck, one host trying to DD an image across the network. Better than that, let's make each of the bare metal nodes actually fetch the image from Glance or Swift and write it to local disk directly. Those things are already scalable, so great. We just get the benefits. For the ops guys, the people who are actually running data centers, things like being able to plug in a rack and have the cloud automatically discover all the hardware in the rack you just plugged in and give you a list and be able to compare it to a spreadsheet you got would be really cool. Being able to do firmware upgrades of the hardware that Nova's running on, or something's running on, and reboot back into the image that was already running on it. These are things that we will want to do eventually to facilitate large-scale operations of data centers using a bare metal driver. I haven't talked yet about the network issues. If you've got OpenFlow-enabled switches, things are pretty easy, pretty awesome. If you don't, and a lot of people might not, then we need to actually know what the physical constraints of the network are before you can boot images or instances on bare metal. Basically, all of OpenStack currently assumes things are virtualized. MAC addresses are just made up on the fly. We don't really care what VLANs are, we just specify them in Quantum and it works. Except if your switches are configured certain ways, and then you have to make Quantum tell Nova the same information, the same VLAN, MAC address, IP ranges that the operations team has actually configured the switch for. So we need to add that. Robert over there is making good progress on it. Just local persistent storage with Cinder or something, so that you can do things like have the physical hardware, have your image in one partition, and all your data stored on another partition, and just re-image the machine, but keep the local storage there. It'd be interesting. Orchestration. There's a heat talk. I saw the devs over there earlier. Being able to, once we can do this imaging at scale of physical machines, then using heat, basically AWS cloud formations, things like that, to stand up hundreds, thousands, whatever, huge number you can imagine, of physical machines in an orchestrated fashion with different services. Other people were talking about that earlier. But not with VMs, with actual hardware. Would be really cool. And then finally being able to deploy an OpenStack cloud using OpenStack. And I think Robert's going to talk about that on Friday quite a bit. He's nodding his head, so yes. So I won't talk about that now. So if you think this is awesome and you want to play with this, this is basically what you need. You need some hardware, You need a flat network, no DHCP, because Quantum wants to own that, and we need to do TFTP booting with our own DHCP server and so on. And DevStack, because that's an easy way to get a cloud going. But maybe you don't have a rack in your closet. I saw hands go up earlier. Maybe everyone in here does have a rack in their closet. I do. If you don't, then you can mock the hardware with virtual machines and actually run everything I just described on your laptop. Yes, some RAM. We are. Yeah. We're mocking IPMI by using SSH and issuing versh commands. So the bare metal driver it's very pluggable, so it has subdrivers. So the imaging process, PXE, we could also, there's a patch up there that's broken right now, but someone should fix it, maybe me, to use NFS and shared storage for imaging things and booting off network volumes, basically, instead of PXE. Instead of IPMI, you could have a PDU driver. We implemented a versh driver, basically. It also works with VBox. We're going to probably plug in parallels and other things eventually. So there's basically a walkthrough that we, as we're developing this, keep up to date at that link for how to do all this in the laptop, in your desktop, in some workstation that you use that isn't a rack in a closet with a big network. If you want to get involved, basically all our stuff's up on GitHub and OOO. That is anything that's not merged in OpenStack trunk. We're working as close to trunk as possible. We're all on IRC, Freenode, ##OOO, and if you want to talk on the mailing list, please use those 2 tags. And that's it. I'll link to them. Sorry? Yep. Questions?
Just in terms of hardware scalability, with virtual machines, I can over-provision my hardware and whatnot.
Yes. So
how does that work with bare metal?
Okay, so with bare metal, there's a different scheduler. You have to enable in Nova. Basically, the Nova Compute agent normally advertises whatever resources are available on that machine. In this situation, when you inform the Nova Compute agent of the hardware available, it advertises each of those as though it were a compute resource. When that gets allocated, it uses 100%. So no overallocation. I saw questions up in the back.
I think that more or less answers the question that I had, because I was wondering, whenever you showed the kind of architecture diagram of the agent perspective, like I can imagine how everything conceptually maps to Nova except for the IPMI power on. But I think you just answered that it's actually that you hard code the availability of physical devices and then you have a custom scheduler. I mean, does that make sense that everything seems to be consistent with how Nova Compute works now, except IPMI, because you're going to have to issue against a specific piece of hardware?
So there's a hardware awareness that is baked into the bare metal driver that we're trying to integrate with other teams that have hardware awareness, like Health and Mon or Ceilometer or whatnot. But basically, yes, you have to know about the physical hardware. So the scheduler picks a physical machine, which you already know the IPMI info for, I assume.
Do you have a solution for our network boot on EFI yet? Because I've been trying to find some Pixie bootable type thing for EFI and just haven't found one yet.
I'm going to punt that to Robert, I think. Okay, nope, we don't. Anybody else? Nope. Okay. Thank you.